Good afternoon, one and all. Welcome to the session. I think we have discussed something in the previous day. We'll be continuing from there only. Am I audible? Hello. Anyone can type a message. Am I audible? Okay. So thank you, Sriya Devi. So we'll be starting from. We'll start with the GIS data models. I think we have discussed a few concepts regarding GIS. What is GIS? What are the different components of GIS, and what are its organizational structures? I think we have completed that. So we'll s- uh, we'll start with the data models in GIS, and okay, so data models. Data models. Now, before getting into the data models, now let me really clarify it. There are two types of data mostly. First one is your spatial data, and second one is non-spatial data. I think I have introduced the data types even in the previous day. So spatial data are basically divided into two data models. One is your raster data model, and one other one is your vector data model. So this is what we'll be discussing today, and we'll get in detail about what is a raster data model and what is the structure of a raster data model. And if time permits, then I will simply show you uh, what are the different types of raster data and what are the vector data. I will take the help of QGIS, and I will show you how the raster data structure basically looks and how the vector data structure basically looks. Okay, so let's get into it. Um, what is the concept and definition of data model? So in GIS, a data model is basically a structured way to represent the real world geographic features. So in a digital format. Now it basically defines how spatial data is stored, organized, and how it is basically manipulated within a GIS system. So a GIS data model serves mainly two purposes. So one is representation and another one is analysis. So what is representation? It basically provides a structured way to represent real world objects. You can take examples of roads, rivers, and land use. So that is how GIS data models basically help in terms of representation. And analysis, it basically enable us for spatial queries, different calculations, and even helps in finding out the relationships between different geographic features. So mostly in a data model acts as a bridge between the real world and the digital representation, and that basically allows GIS um, to store, process, and even analyze spatial data efficiently. And there are different types of data models. There are four types. One is your logical data model. So logical data model basically describes how data is conceptually structured and organized independently of what any specific database or software. It focuses on relationships, rules, and constraints between different data elements. So this is what logical data model is about. I mean, let's take an example. we might define a road network, so which is consisting of roads, basically those are basically the lines, and now connected at intersections. So intersections are basically your points. So this basically represents lines and points. So this is a road network. Then another example can be a land use system or land parcel system. So where each parcel or each use or each area is associated with some kind of attribute data. I mean, I was giving example of a school in the previous day. Now, where school is basically located, now we can also take example of a village. So village is basically a spatial phenomena. Now where the villages do, now that village do have certain latitudinal and longitudinal extension, and that basically is an area. Okay, that basically is a region. So it is basically a polygon. Okay, so this is what no how logical model basically helps in GIS. So logical models basically help in understanding how data elements relate to each other, before they physically stored in the database. So that is the use of a logical data model. Then the physical data model. The physical data model basically defines GIS, how data is actually stored and implemented within a database or file system. Data formats like, within raster data model you do have geotiffs or tiff or maybe geo packages, and whereas vector data formats can be, zip files, geojson. So all these are different data formats through which a physical model basically, store and implement the data. Data structures. That data structure within a physical model basically includes different tables, indexes and file directories, so file paths. So those are basically storage structures within a physical model. And you can also compress and optimize to improve the efficiency. So this is how physical model also helps in your data model. Examples can be, physical model might define how a vector data set is stored in a geodatabase. I mean, both both vector and raster data sets can be stored in geodatabase, while vector data sets are really efficient in storing in the geodatabase. So no, while specifying attributes like file size, coordinate systems, indexing. So all these are basically the physical models. Object-based models. So within object-based models, geographic features are basically treated as distinct objects. So with a specific location and attributes. So geographical features like any geographic features, buildings, different types of soils, any area, anything. Okay, so these kind of geographic features are basically treated as objects, so within a specific location. And these models are used in a vector data format to represent features as point, line and polygon. So a vector data model itself is defined by these three data structures, so which are basically point, line and polygon. And what are the different properties of object based models? Now each feature has an unique identity, and attributes are basically linked in a relational database. Okay. Examples like roads, rivers, buildings, and different land use, land cover. Then these models are basically used in urban planning, this object based model, urban planning, transportation, and even in cadastral mapping, we use these kind of object based models. Then what is field based models? So field based model, geographic phenomena are basically represented as continuously varying fields across a surface. So this approach is commonly used in raster data models. I mean, vector data will basically represent one object at a time. So basically objectifying any feature. Now, while raster data model basically help you um, continuous representation of any geographical phenomena. Now, just like the vegetation cover. So the vegetation cover, within the vegetation cover, you can actually, if you guys know what normalized difference vegetation index is, that the values basically varies between -1 to +1. So different groups of those values will represent different categories of vegetation. I mean, if it is closer to 0 or -1, then it is basically representing very uh, low vegetation cover. Now, while if the ndvi values basically exceed 0. 0.5 or 0.6, so and remember, the pixels are basically representing these values. So then it basically represents that the vegetation cover is really high, and there is dense vegetation cover available in those geographical regions. So this is basically a field based model. Now, where each cell is basically the pixel of any image. Okay, so each cell basically contains a value so that represent a continuous phenomena. Now, just like elevation or temperature or maybe soil moisture or evapotranspiration. So how these are basically represented as pixels, or these are basically represented as cells. Now, because within digital elevation model, so which is basically represent the elevation of any region. Now they are basically, you'll be seeing each pixel basically represent a value. Now, if uh, um, any raster format, so which is having a resolution of 30 meters, and each pixel will be having some value. So if one pixel is having a value of around, let's say, 300 meter, then that place is basically representing that that region is uh, more or less having an average elevation of 300 meters. So it is continuous in nature. Now, because I'll show you a digital elevation model in the QGIS. And field based models are widely used in environmental analysis. Okay, and even climate modeling. Now a lot of researchers are um, taking interest in climate change studies. So these kind of data sets are really helpful in uh, in analyzing and interpreting different climatic variables, or building any kind of model. So this field based models are actually helpful in these kind of studies. Okay, so data models, raster and vector data are basically um, raster and vector data are basically the spatial data models. So within raster data model, it basically represents geographic space as a grid of equal sized cells or pixels. So here you can see. So if this is the raster data model. So here, one pixel. So if you do have an image, and it will be having some resolution. Okay, so each resolution, I mean, if you zoom in to the max, to the maximum, then you'll understand that these images are basically made out of different cells or different pixels. So this is how it has been represented, you know. So these are basically columns, these are basically rows, and you'll be having resolution. So resolution is basically what is the size of that pixel. The size of the pixel basically represents the resolution. So each pixel will be having some value. So this is the I think the example has been given here for IRS P6 satellite sensor LIS 4. So LIS 4 is having a resolution of 5.8 meters, and LIS 3 somewhere around 24 meters. So LIS 4 is more advanced, and it gives data in a more detailed way. So if you do have list for imagery, I don't have one right now. So if you have list for imagery, it can actually give you a lot of information, in a more detailed manner now, because the resolution is really high. I mean, you can differentiate between different geographical objects. I mean, different objects can be differentiated when the pixel size is large. I mean, when the resolution is high. If the resolution is very coarse, and take the case of, let's say, 100 meters. So within 100-meter, a pixel will represent a lot of geographical features. So in a way, what will happen, it it becomes really difficult for us to analyze and interpret those kind of raster data. And if you want a detailed study, then you'll be needing the data, and that should be of high resolution. So where raster data models are mostly used or commonly used, so DEM here, it has been given example of a digital elevation model. So digital elevation model is basically a model that represents the elevation of any region. I mean, through this digital elevation model, we can find out now which regions are having what elevation from the mean sea level. So different data sets are basically available for different digital elevation models are available to us freely. Now SRTM, so which is NASA's data, subtle radar topography mission, so which is of 30-meter resolution. Now even coarser resolutions are also available. Now the previous version of SRTM was of 90 meters. Now it is providing you 30-meter resolution dataset. Now even we do have our India specific satellite data for digital elevation model, Cartosat 1, I think, which provides you uh, 5 to 10 meters of digital elevation model data, but it is paid. And you can use Cato DEM, so which is of 30-meter resolution. So 30-meter resolution data is freely available. Then Aster data, or Aster GDEM, so which is also one of the most popular digital elevation models available to us. And it is basically advanced space-borne thermal emission reflection radiometer global digital elevation model, so which is also available at 90 meters and 30-meter resolution. Then Alos Pulsar, Alos World 3D. So it is also available at 30-meter resolution, but Alos Pulsar is um, another data from Alos, and it is of 12.5-meter resolution. Uh, Here also Cartosat 1 provides you 2.5-meter resolution data. Okay, so which covers more than 80% of the country, and it is a paid data actually. But the Cato DEM, which is of 30-meter resolution, is free data. Uh, what is what are the different types of raster data? You have discrete raster data. so which basically represents categorically data within distinct classes. So examples can be land use maps that basically represents forest, water, then soil types, different types of soils, then administrative boundaries. um, the values are basically integer based, representing different classes. Now, as we have already discussed that now each pixel will be having some values, so that is mostly integer based values. One is your discrete raster data, then second one is your continuous raster data. So continuous raster data is that basically represents gradual change across a surface. So when you have gradual change across the surface, just like elevation, temperature, precipitation, then the vegetation index, so those basically change gradually um, from a place to another. So that kind of raster data is basically continuous raster data. And raster resolution and scale, you will be having high resolution data and low resolution data. So if the cell size is very very detailed, and it basically requires high storage facilities. Now, because if you want, let's suppose the list 4 image which is of 5.8 meter resolution for one district. Now you may require few GBs of data storage. Okay, so that can store. And now for the whole of Odisha, now if you'll be capturing the satellite imagery of list 4, which is list 4, then it will be requiring a lot of data. So if that is one of the disadvantages also. Now we'll be discussing about the advantages and disadvantages. Low resolution rasters are basically where the cell size is very large. I mean, let's say 200 meter or 500 meter resolution data. I mean, if one cell will uh, represent 200 meters of geographical area, 200 square meter of geographical area, so it will basically average out the features which are available within it. I mean, the digital. Now we can take example of the digital elevation model. So now let's suppose take the case of the Khurda district. So if we do have a digital elevation model of Khurda district of 30 meters and another one of 90 meters. So the 90 meter the 90-meter resolution digital elevation model will definitely be showing some errors, or some, it will be missing some minute details or information regarding the elevation of a particular place. Now, because the few pixels will come of 30-meter resolution within that 90-meter resolution. Now, because each pixel will be having some values, and each value will basically represent a data, and it will give us information. So based on the information, we basically interpret that data and analyze the data. Now, if the resolution which is available to us is really coarse, I mean 200-meter or 500-meter, so then what happens, you do not get a um, proper information of that region or of that cell. Now now where basically these low resolution data sets are helpful. Now when you are analyzing for the whole of Odisha, or maybe for two to three through three states, or maybe for one country, and the computational efficiency is really low. I mean, you don't have the computers to handle those kind of data sets, then the coarser resolution is helpful, or maybe the low resolution rasters are basically helpful, or else using high resolution data is better for detailed analysis. So what are vector data models? These basically represents geographic features using point, line, and polygons. So unlike raster data models, so which basically divides space into different cells or pixels. Okay, so into grids of cells and pixels. So the vector model no stores spatial features as precise geometric shapes with associated attribute data. Precise geometric shape, I mean, you will be requiring line, a point line and polygons to basically show few geographical features. Now, just like roads or rivers, so these are basically represented as lines. So here we can take example. Here it can be a road, it can be a river, or this kind of linear features. Wherever is available, so we can use the vector data model to represent these kind of data. Or then you have point data. I think I was giving example yesterday about the point data. So point data basically the uh, represents any point, any geographical point. I mean, if any schools, any post offices, a railway station or a bus stand, so all these are basically points. So that will be having no one latitude and longitudinal value, so that will be represented as point. Now why these data sets are basically different from that of the raster data model? Now because these are not continuous in nature. Okay, so now although line feature and polygon features can be continuous in nature, but they do have only geometries to save different information. So these are basically shapes that store information of that particular feature, geographical feature. Now if you want to identify the area which basically receives high amount of precipitation, then you may do one kind of study that these regions are basically, we are using contours. Okay, so contours to represent the elevation, isoheights to represent precipitation. So likewise you can do interpolation. I mean, there are different interpolation techniques which are available to us, through which we can rasterize any input data. So through methods like kriging, also different types of kriging are also available. You have geographically weighted uh, kriging, then ordinary kriging, and advanced kriging. So all these are different techniques of uh, interpolation. And even IDW, inverse weighted um, inverse distance weightage. So that is IDW. I think here it has been given inverse distance weighted. Okay, so kriging is another interpolation technique. Then spline also is used. Spline is basically used when the data structures are basically very linear, and IDW is one of the most popular interpolation techniques that is right now being used by a lot of people. But the kriging is much more advanced. And now why? Now because it takes into consideration the the spatial autocorrelation. Now because IDW neglects that. IDW do not take into consideration the autocorrelation of the geographical space. So that is why kriging is much more accurate as compared to the IDW. Now when interpolation uh, is the case. Okay, so what are the basic elements of vector data model? So you do have point features. So one point basically represents single location with no dimensions. Okay, um, so it will be having some x and y coordinate. Okay, so any point will be having some x and y coordinate. Example, wheel locations, even city points, and bus stands. Okay, so each point has attribute data that describes it, such as well depths or city's population. Okay, so I don't know, you let's take into consideration any bus stand. So let's say Bermuda bus stand. So Bermuda bus stand is basically a point where some attribute data are basically attached. You can consider how many buses are basically um, within a day, how many bus basically give services. Then what is the highest number of buses, in what time, highest number of buses they basically cross the Bermuda bus station. Okay, so these are basically attribute data, and how many people are basically getting the services from that bus stand. So these are basically the attribute data. This is a point feature. Then you have line feature, which is also called as polyline. Okay, so it basically represents linear features that have length but no area. So that is what line represents. Now the side boundary of any road or any river. So if you are representing a line of river banks, so then those are basically considered to be the polylines. Okay, so that is one kind of vector data. Then you have polygon features. Okay, so polygon features basically represent closed areas with defined boundaries. Now examples can be land use patterns, okay, lakes, even administrative zones, forest boundaries. So all these are basically polygons. I mean, the district boundaries are basically represented as a polygon only. Okay. Okay, let's take the help of QGIS, and I will show you different types of vector data and raster data. So these are basically vector data models. So I am here having point data. So different cities, okay, or major towns are basically shown in this data. You can see here. Okay, so this is the boundary of Puri district. So within Puri district, we are having these cities or these major towns. Now, starting from here, you have Pipili, Nimapada, Gop, Delang, Kanas, Sakhi Gopal, Puri, Brahmagiri. So all these are basically major towns. So each point, so these are basically points. Okay, so each point basically represent one um, data here. So this is a point data within a vector model, and within that you can have different kind of attribute data. So if I'll be opening the attribute table, so I can see, now which is this data. Sorry. Okay, so within this we can look into what is the name of that town, then which is the district. So which is the district is basically an attribute data. So now take the case of the Nimapada. So Nimapada is basically a town, so that has been represented as a point vector of point data within vector model. Then within that we are having, district as one of the attribute data, even the state as one of the attribute data. We can include elevation, we can include rainfall, we can include population or population density or anything. So these are basically attribute data which supports the point data or supports the vector data. Then polygon are basically closed set, just like the boundary of the Puri district. So here is the boundary of Puri district, where we can clearly see that this is Puri district. Okay, okay, so this is your Puri district, and this is closed now because it is a polygon. Let me see if I do have some line features available. Just a minute. Okay. Yes. uh, so this basically these are line features. Okay, so here uh, this is derived, these streams are basically derived out of a digital elevation model, and all the low points are basically considered to be the continuous low points are basically considered to be a stream here. Okay, so these the major sections are basically still streams. This region is a part of the tail basin, this region, and the whole of Balangir district is also a part of the television. So these are basically lines that basically represent the lowest elevation point within that region. So if the I think you know about, being a student of geography, you know about what do you mean by a catchment, what do you mean by a watershed. So the catchment is basically derived from these regions. No, I mean, if this is a river, so then this whole area is basically a catchment. Okay, so here, the this area is the catchment area is basically a polygon. Okay, if we will be delineating that catchment area, then this will be considered as a polygon now here. But the streams are basically the polylines. Now if we'll plot some um, major towns of that region, then we can simply say no different towns of Balangir district. So that we have already discussed also. Okay, anyone is asking something? Susanta? Okay, then let's continue if no questions. Okay, so then you have topological models. So within a vector, the vector data basically can be topological or non-topological vector models. So what do you mean by a topological vector model? So it basically stores relationships between features such as connectivity, containment. Examples can be road networks where intersections are explicitly defined. So those are basically topological vector models. So that basically helps in network analysis, shortest path calculation, or even spatial integrity. Now, while non-topological models basically stores geometric data without relationships. Okay, simple zip files without connectivity information. So it is really easier to store and manage, but it basically lacks different advanced spatial relationship. Okay, so then let's get into what are the advantages. Now, here. A comparison has been made for the raster and vector data models. Data structure is really simple for raster. Now, why? Oh, now because it is continuous in nature and it is basically stored as pixels or cells, and it is really easier. Now, while the vector data models are basically complex, now because it stores as XY coordinates, and it is also relational as compared to the raster data model. Storage, I think the vector model requires low storage as compared to the raster data model. The raster files are often really large, so that is why it requires significant amount of storage. Data conversion, definitely, if the file size is really high, so which is in the case of raster data model, definitely the data conversion will take a lot of time, and in terms of compression, or maybe to reduce image sizes. But the vector data model is really fast data conversion, and access, you require high computer processing power to access the raster data models. Now, while you may not require much high computer processing power to access um, this kind of vector data models, analysis is easy, really easy for continuous data, while it is really complex for the vector data model. I think we can take an example. Uh, so here is a digital elevation model. Let me properly show it to you. Okay, so this is basically a digital elevation model. Within this digital elevation model, we can clearly see, which are the regions which are highly elevated and which are the regions which are having low elevation. Here, you can look into these regions. Okay, so these regions which are in brownish color and yellowish color, so these basically represent that these regions are having a no high elevation regions. So this can be clearly visible if we can add one of the hillside maps. Okay, so now it is really easily visible. I mean, which are the regions which are having high elevation and which regions are having low elevation. Now, even you can categorize it. I mean, we can simply divide all the continuous values, so which is available from 125 to somewhere around 933, so into equal intervals. So within equal interval, you can increase or decrease the number of classes that you want to see. So between the high and low elevation values, this function will basically categorize the data into 5 categories. So within the 5 categories, you can see here, which are the regions which is having, what range of elevation. Okay, so from 0 to 299, so this sky blue color is basically representing this region, and most of the regions are basically under you know 299 meter of elevation. And these regions, the the green regions are basically between 299 to 472 meter, and the yellow regions here uh, are having more than 472 meters up to 646 meters of elevation. And this black region do have the highest elevation within within the whole of this district. Okay, so these are basically this is basically how a digital elevation model look. Okay, so if we will zoom in to a point where we can clearly see, there are a pix there is a pixel. Okay, so here it may not be clearly visible to you, but here there is a line. No, each pixel will be having some values. So that is why what happens, each pixel, these are the pixels. Some are really dark, some are maybe we can give some color so that it will be visible. Okay, now it is really, easily visible to our eyes. Here we can clearly see these are square shaped boxes. So each cell, this is basically a pixel. So each pixel is basically representing um, an elevation value. So which will be integer based elevation value. Maybe this region is having an elevation of somewhere around near to 500. So that is why this is the color that has been assigned here. Now this is basically a color ramp. Okay, so this is a color ramp. Now these green regions, and here we can also see some square shaped boxes, so which are the cells, and these are of higher elevation. So if you will be comparing this region, okay, this region within the district with this region of that same area, then we can clearly differentiate between these two regions, that this region is basically having high elevation as compared to this region. Now because it is clearly represented by the light red color and the light greenish color. Okay, give me 5 to 10 minutes, then I will be back. Hello. So welcome back. We will continue with the data structure. So data is basically structured in two primary models. So raster data model and vector data model. So each model has its own way of storing and organizing spatial data. The choice of data structure basically depends on the type of geographic features being represented or the intended analysis. I mean, first, uh, and what kind of analysis you basically want. Based on that, you'll be choosing, which data model that is basically needed. Now, just like if you want the elevation information in a continuous manner, then you will be needing raster data model. Now, let's suppose you do have point data in vector format and you want the elevation of those particular regions or those particular points, then that is one kind of attribute data that is related to or attached to that vector format. Let's first understand the raster data structure. Raster data structure represents basically a geographic space using a grid or cell or pixel. So, which is basically we have defined raster data structure. The arrangement of these cells basically determine how data is stored or processed. Simple data structure basically follows grid format, the raster data structure. Most of the basic form, so which each cell is stored within a matrix. Okay, so that is what raster data is. The position of cell is basically determined by its row and column number. We have already seen which is a row and which is a column, and what is the position of a cell. So here, these are the rows, these are the columns, and each of these square boxes are basically cells or pixels. And the value of sales basically represent an attribute. I think as we have seen in the digital elevation model, each pixel will be having a value, and that will represent the whole of that geographical area. uh, okay, so this is basically simple raster data structure, so which is in grid format. So another raster data structure is basically run length encoding, RLE. So within run length encoding, the data are basically stored by grouping consecutive identical values instead of storing individual pixels. So it is more efficient for areas with uniform values. Now, just like here, now if we will categorize this data into discrete classes and with equal interval, if you'll be showing or representing the data into 10 classes, so definitely now here we can clearly see that this region is very low elevation region, and simply this region can be considered as a run length encoding. Okay, now because we have grouped the data into some regions and each of these are basically representing some values. Okay, so and it is more efficient for areas with uniform values. Now why? Now because now these regions are having almost equal values. Now even though we have classified into 10 groups, but these regions are having equal values. Now if we will be considering this as one pixel also, it is fine. Now because these regions are basically representing values between somewhere around 212 to 299. Okay, so these values are basically or maybe below 212. So these values basically represent that kind of elevation data. So, and this run length encoding is basically helpful for a very large area analysis. Now, where similar groups are or similar cluster of data are basically available. Then quad tree data structure of raster. One is your simple grid, the grid data structure, which is the simple format of raster, where each um, where the data is basically stored in cells or pixels. Then you have run length encoding, and then you have quad tree raster structure. So it basically uses hierarchical tree structure to divide the raster into quadrants. Okay. So quadrant, I think we can also divide the data into quadrants. Um, Whether the function is available here, let me check. Quantile function is available, but quadrant is not available. But still, you can see. Okay. So here you can see clearly see. You know, now this is basically a hierarchical tree structure, so which divides the raster data into quadrants. So areas with uniform values are basically stored as single unit, while detailed areas are further subdivided. And it is efficient for compressing large raster dataset with varying levels of details. Examples can be this region, let's suppose this region is highly elevated, but it is within a range, and you want to analyze, you don't actually require a very fine or detailed explanation. So then you can simply use it. I mean, a region with uniform elevation, so which can be stored as a single block. Okay. What are the advantages of using this kind of quad tree raster structure? So it is really efficient, and it is it now we can fast processing in overlay or even different raster calculations, and it is also compatible with different remote sensing applications. Okay. Then vector data structures. So within vector data structure you have a spaghetti model. So a spaghetti model is one of the most simplest forms, now where features are basically stored as independent geometric for objects. Now no relationships or connectivity analysis, uh, or connectivity between features. It is commonly used in CAD system and early GIS softwares. And right now, spaghetti vector model are rarely seen. Roads basically stored as individual line segment with no intersection relationships. So this can be an example. Now, if without any intersections, if roads are basically stored, then this is basically a spaghetti model. Then comes your topological vector model. So within topological vector model, what happens? It basically uses nodes, edges, and faces to define relationships, and these are essential now because these topological features basically essential for network analysis. You want to calculate the shortest path between two points, then you will be needing nodes and edges, so which is not available in spaghetti model. And it stores spatial relationships basically between features, such as urgency and connectivity. Then Teen structure. Teen is basically your triangulated irregular network where a vector based representation of surface that basically uses irregularly shaped points connected to form triangles, efficient for basically terrain modeling and elevation analysis. So teen, the triangulated irregular network is really useful in elevation analysis, and this is a popular model for elevation analysis only. And most of the uh, hydrological studies which require um, a robust data set for elevation, they basically uses tin. Okay, so the concept of geodatabase basically stores uh, stores all type of GIS data formats into one. And within ArcGIS, now here actually the ArcGIS example has been given. Now while I don't have the ArcGIS here, uh, within within Arc catalog, there is a software Arc catalog. Within Arc catalog you can clearly see geo databases are basically created on default. The geo databases are basically created where you can save different raster files or vector files for one of your projects. Now if you are doing a project on let's say climate change, and you are analyzing different parameters or climatic variables, just like precipitation, temperature, maybe pressure, air pressure, and evapotranspiration, anything. So those kind of data can be easily stored in a geo database. Now just like I think I was giving example of partitioning your drives to store different types of informations. Now where you now here you don't have to partition any drive. You'll just have to store that geo database within the system, and that geo database can actually store different vector formats data. I mean, you within your analysis, if you are considering different major towns, different different district boundaries, so all these can be stored within that. And if you are analyzing precipitation, then that will be basically continuous in nature. So those continuous data, I mean, will be in raster format while the boundaries will be in vector format. So all those data can be stored within the geo database. So types of geodatabase, personal geodatabase can be there where you basically use to store. Then you have enterprise geodatabase. So enterprise geodatabase basically allows you to access the database which has been stored in the server. Okay, so different different data management systems are there which basically provides you these kind of geodatabases. I mean, you can look into Oracle, you can look into Microsoft SQL server or SQL. No, I was giving example of yesterday only. Now where you can get your data. So this block is about GIS database creation and spatial analysis and outputs. GIS database creation, spatial analysis, and output. So here, what are the different data inputs? What are the different methods used? What are the different tools available for data input? Then what are the different data standards? Then data acquisition. How can we, access data, then attribute data and how to manage it, then data quality issues. So all these we'll be discussing here. Here data input methods, uh, which are the different data input methods. um, there are mostly two main ways to input raster data into GIS. Either you scan hard copy maps, or that is basically the rasterization process, where you scan any kind of paper maps or photographs, so then into digital raster format. So that can be a graded image. I mean, the JPG format or PNG format or TIFF format that we are basically using for images. So those are basically pixel based formats. And remember that the scanned images must be georeferenced. We'll be discussing about the georeference. Then direct raster data capture. First one is scanning and rasterizing any data. Then you have direct raster data capture, where we'll simply download any data set from the satellite. Okay, so from the server, so which is basically being hosted by different organizations. Then aerial photographies are also helpful in um, data accessing. Okay, so and these are basically raster data input methods. What are the different vector data input methods? So within vector data input methods, we'll be having manual digitizing, I mean vectorizing. So if you want to uh, if you want the uh, river bank line, okay, so you can manually digitize it from any image. So that is basically the process of manual digitization, or we basically call it as vectorization. Then direct vector data and collection, so where you can use GPS. Okay, so where you can capture the point data. Then there is an instrument which is total station, and even drones, so that can actually capture you vector data. Then right now we are having another method, automated vector data extraction from remote sensing. I mean, uh, automatic extraction can also be done, or automatic vectorization can also be done. So using artificial intelligence, now right now the AI is really popular. So with the advent of large language models like ChatGPT and different copilot models, so now AI is really helpful even in remote sensing and GIS. Now another AI vectorization is also helpful now, although it sometimes hallucinate. That is one of the major issues of artificial intelligence. Or else it is really helpful. I mean, if now wherever it will be hallucinating, you will have to manually correct it or rectify it, or else it is fine. I mean, it can save you a lot of time, the AI vectorization. Then you can simply import. Another method can be, you can simply import existing vector datasets. So if some pre-existing vector datasets which are basically available in government agencies, or even from research institutes or online repositories, so all these datasets can be directly imported. I mean, there is a platform called Diva GIS. Okay, so within that you can download different zip files. So here within Diva GIS, let's suppose you want to um, download the political boundary of India and administrative area. I want only the administrative area. Then the format, you'll have to, yeah, here. Okay, so I can simply download it, and so these are the pre-existing CEF file formats which are available to us. So this is Indian administrative boundary, and if let's unzip it first. Okay, so here are the CEF files. Let's see what this CEF file data is basically. Okay, so this is the political boundary, administrative boundary, political administrative boundary of the whole of India, and we can clearly see it. Sorry. Okay, so for better visualization, you can add any base maps. Google Satellite is fine. Okay, so now we can clearly see this is the Google satellite imagery, and this is the boundary. This is the boundary of the whole of India, and this is geo-referenced. I mean, or else it cannot be overlaid on the Google satellite imagery. Now you can clearly see that this is the boundary. This is the coastline, or else there will be mistakes. I mean, you will not see it, so that's the problem. These are the state boundaries, so within that we can clearly see the state boundaries. Okay, so this is here Odisha, and you if you want to really see some features, then you can clearly see it. This is the Hirakud reservoir, and here we are having the Rengali Dam, and Rengali Gorge, the gorge that has been created by the Brahmani River, and this is Satkosia Gorge. So where Mahanadi basically enters and cuts deep through the eastern Ghats. Okay, so this is your lower Mahanadi region, and these are the deltaic regions of Odisha. And we do have a composite delta now, because the Brahmani, Baitarani, and Mahanadi, they all together basically makes this compound delta. Okay, so from just like Diva GIS, we can use other platforms which basically provide us different set files, or uh, even Survey of India do provide us different set files of administrative boundaries up to I think up to village level also. The village level set files are also available in Survey of India for India. Then OpenStreetMap is another popular no GIS portal, from where you can actually download different kind of data. I mean, it is basically a base map. The open street map, OSM. So this is one of the popular open source data which is available to us now, because it will be showing you different road networks, and all the physical features are also available. Then different building footprints are also available. And here we can clearly see Bhubaneswar. Okay, so you can also download the building footprint data from the open source, sorry, open street maps. And this is how it is really helpful. I mean, these are the road networks, and this is the railway line, this is the airport. So all these data are available. Then what are the different input devices? uh, so first, you do have scanners. Scanners basically used to convert paper maps or aerial photographs or even hard copy documents into digital images. And scanned maps that must be georeferenced to align them with the real world coordinates. I mean, uh, just like this here. Okay, so this is the boundary of Odisha. If if this vector format, so if this vector format is not georeferenced, then what will happen? You know, when I will toggle on the Google satellite image, then all the features which are basically available or which are basically seen within the boundary of the Odisha may not be available. I mean, there will, if it is not geo-referenced, what does that really mean? You know, the real world features will not be available within that boundary. So there will be some mistakes. So that is why geo-referencing must be done before proceeding. Okay, so scanners, then you have digitizers. So within digitizers, devices that help manually trace, you know, geographic features from hard copy maps into vector formats. So scanners are basically used for raster formats, while digitizers are basically used for vector, making vector format dataset. Then GPS is another device, so which is basically used for, so which is basically used to collect the point data or even line or polygon data directly from the field. We can directly download the data from the field itself. Now, because this is a survey tool. Then total stations and theodolites. I think even in UG you might have done some practical exercises on theodolites. I think total station is really expensive, and most of the geography departments I haven't seen total station. So this is one of the land surveying tools or instruments. Then drones and lidar sensors. So drones basically, right now the drones are being used to capture data. So this is basically another input device. So how can we create new data? First of all, we can digitize any maps for creating any data. Uh, uh, even mobile GIS can be used. Crowdsourced data collection, just like I have given example of OSM, OpenStreetMaps. So from OSM also we can download different data sets regarding roads or maybe population. Even population data is available. Even different administrative setups, the building footprints, and other kind of data is also available. So what are the different methods of in situ data collection? Okay, within that we have GPS based surveys. So where GPS units or mobile GIS apps are basically used for collecting different point data. Then that can be combined with attribute data collection for mapping infrastructure and environmental features and even land use land cover classes. Okay, so examples can be, now let's suppose you want to analyze the groundwater quality, or you want to monitor the groundwater quality. So what you can actually do, you can you can survey with a GPS device. So that will basically give you coordinates of the point that you are collecting data for groundwater. Then you can simply interpolate it later on. Then GPS after GPS you do have a mobile GIS, and remote sensing also do provide us the in situ data. Then drone surveys can also be done. That is okay. Let's have a look at map digitization. Okay, so within digitization, uh, we are basically creating different point line and polygon features. And here maybe tomorrow I'll show you now how to create vector data formats and how to digitize the data, and which may be useful in later on. You may require that, and you may analyze them later on to maybe study something. Okay, so reference framework for GIS data. What do you mean by reference framework? I mean, uh, each each of these kind of datas will be having some reference framework. So in GIS we do have a coordinate reference system, which is basically CRS. And coordinate reference systems are basically of two types. One is your geographic coordinate system. Now right now we most of the GIS data sets, they basically use a default uh, of no WGS 1984 marketers projection. Sorry, not marketers. It is basically WGS 1984, the geographic coordinate system that we are using, and the projected coordinate system. So, which is another type of CRS, which is which no, the geographic coordinate system is really helpful for locational accuracy. Now if you really want locational accuracy, then you need to use the geographic coordinate system. Now while projected coordinate system actually helps you in understanding other dynamics of that data set. Now let's suppose you do have a CEF file, the boundary of, let's say, Odisha, and you want to know the area of that CEF file, um, I mean the polygon CEF file, then you can simply calculate it. Now if Okay, so I was discussing about the geographic coordinate system, and also about the projected coordinate system. So projected coordinate system is really helpful in those areas. uh, just like if you want to calculate something, the area of any polygon file, then uh, for Odisha we basically use 45N UTM 45N universal transverse marketer, and the marketer projection is basically used for this projected coordinate system. Now, although other coordinate systems are also available, but we basically stick to these two kind of reference systems. Geographic reference system. So where we basically mostly use WGS 1984, and for projected coordinate system we basically use UTM, Universe Transverse Marketer. So this is it for today. Maybe tomorrow. I think tomorrow is holiday. A day after tomorrow, we will be discussing how to create CEF files and the block 3, sorry, block 4. Now, where I think block 4 is about spatial analysis and outputs. Okay. So within spatial analysis and output, we do have GIS data display and exploration, introduction to vector data analysis, and introduction to raster data analysis, then GIS output. So I think we have to some extent understood what are vector data models and what are raster data models, and we'll be looking into how to display and how to explore different data models in GIS softwares, and then how to analyze different vector data and how to analyze different raster data. So maybe day after tomorrow we'll have a go with this, and I will try to keep it more of a practical rather than much of a theoretical. Now if you are actually listening or you are actually watching it, then you can easily understand it. So I will take the help of QGIS now, because natively my MacBook doesn't support ArcGIS. So QGIS is really really good also. I mean, you can also install it in your Windows laptops, and you can have a look at the user interface, how different things can be done and how different GIS data can be handled. And this will be alien to you unless and until you do some practical work. I mean, the concepts of GIS will be definitely be difficult. I mean, we people are not that technical, being the students of geography. I think if some of you have technical backgrounds, then you can really understand it. And now for these kind of no these kind of syllabus, you need to understand different things, technical things. Okay, so GIS itself is really vast, and 4 5 classes are not enough to make you understand what GIS is, and even the remote sensing. I mean, the GIS remote sensing, they are really vast. So for practical purposes, I will show you how to create different vector and raster data formats. Now, for raster data formats, you can rasterize something by interpolating out of the point data that I will show you. Then how to create a point file, a polygon file, and a polyline file, that will see, and how to georeference any existing maps. I mean, if you do have a paper map, that you can actually scan it, and uh, take the help of GIS softwares to georeference it. Then you can extract different information out of it by digitizing different data. Okay, so this is it for today. Thank you everyone.